trickiest part of this chapter, in my opinion, is comparing SN2 to SN1 to E2 to E1. Oftentimes it's not super clear which pathway is going to be favored, but right now we already have the tools at our disposal to predict which ones will be most favorable. So let's make a list. And the first thing I want on our list is a good nucleophile that is not basic. And what are some examples of good nucleophiles that are not basic? So sodium hydride was not a good nucleophile, but was basic. So it was flip-flopped. So what else could act as a nucleophile that's not really a very good base? Does anybody have an idea? Think of the far right of the periodic table. Halogens. So any halogen with a negative charge, it can be a nucleophile, but it's not a particularly good base, right? So if we see chloride floating around its solution in an aprotic solvent, it's not going to be a very good base, but it can be a decently good nucleophile. Same thing is true with thiols and thiol-like compounds. Sulfur in general is not going to be a very good base, but it can be a really good nucleophile because it has a huge amount of electron density on it. So these are good nucleophiles that don't really do much acid-base chemistry. And if we think about our substrates, we've got a variety of different types of substrates. We could have a methyl substrate. We could have a primary substrate. We could have a secondary substrate. Or we could have a tertiary substrate. Do you think something that's a good nucleophile that's not basic is going to do an SN1, SN2, E1, or E2? SN2. So SN2 reactions, we said you need to have a good nucleophile. And in this case, if it's an SN2, what's going to be the fastest? Methyl groups, primary groups, secondary groups, or tertiary? Methyl. So remember, your nucleophile wants the most accessible approach. So your methyl group is only going to do SN2. Same thing with your primary group. So these will only do SN2 reactions. Will a tertiary carbon ever do an SN2 reaction? No. Tertiary carbons will only do SN1 reactions. And then what about secondary? It could do either, right? So in general, if we're looking at SN2 reactivity, methyl groups are the fastest, primary is second fastest, secondary is third, and tertiary is last. Tertiary can only do an SN1 reaction. All right, let's take a look at the counterpart. So this time, instead of using a good nucleophile, we're going to use a good base. Not nucleophilic. And what's an example of a good base that's not nucleophilic? Sodium hydride. What about other ones? DBU. Just rattle off letters, you're bound to run into it. DBN. Alphabet soup. All right, same thing. We can say, all right, we've got methyl, we've got primary, we've got secondary, we've got tertiary. What do you guys think will happen with a good base that's not nucleophilic? SN1, SN2, E1, or E2? E2. Will it work with a methyl? No. We don't have beta protons on a methyl carbon, right? So in this case, we'll get only E2 products. We won't get any methyl products out of this. All right. Now, the last part that's tricky. Or actually, we've got one more before we get to the tricky part. What if we've got a weak nucleophile or base? Something like water or an alcohol. So I'm going to call our alcohol ROH. Could have methyl, primary, secondary, or tertiary. If we've got a weak nucleophile or base, will this favor SN1, SN2, E1, or E2? Oh yeah, this is tricky. Remember how I said with E1 reactions, you oftentimes see SN1, and with SN1, you oftentimes see E1? They're closely related reactions. So in this case, we typically see these occurring with tertiary carbons, because tertiary carbons are the ones that give you the most stable carbocation. You typically don't see them with secondary or primary. So not practical in most cases. But I'm going to put some asterisks there. And in what case can we observe an SN1 or an E1 reaction on a secondary carbon? Resonance. So benzylic or allylic carbons will undergo SN1 or E1. That's one case. What's another case? Yeah, rearrangements. Rearrangements of a secondary carbon allow for SN1 or E1. And then let's say I want to do an E1 on a secondary carbon. What's the trick that we often use? Heat and what else? And acid catalysts. So secondary alcohols will do E1 with heat, which is our delta symbol, and acid catalyst. So I say it's not practical in most cases, but as with everything in chemistry, there are some exceptions we have to pay attention to. Benzylic and allylic cations are stabilized via resonance. Rearrangements will convert a secondary carbocation into a more stable tertiary carbocation. And then secondary alcohols, we said, will often do E1 reactions with heat and acid. All right, the last class. So strong nucleophiles and bases. Oftentimes we run into nucleophiles that aren't just nucleophilic, they're also good at doing proton transfers. Examples of these would be something like an alcohol that's been deprotonated, so an alkoxide, or hydroxide. Both of these are reasonably good bases, but they can also act as nucleophiles, right? And I am going to put a little asterisk next to this R. What's one type of R group that won't participate in a nucleophilic attack? Does anybody remember? Yeah, the tert-butyl, right? So we said that the tert-butoxide isn't going to be a good nucleophile. Why is that? It's too bulky. So if that R group is big enough, it won't be a good nucleophile, but if it's a small R group, it can be a good nucleophile. So let's do the same thing that we did with the other ones. So I'm going to say, all right, methyl, primary, secondary, and tertiary. All right, so we've got something that's a strong nucleophile. That means it could do SN2. Does SN2 favor methyl carbons or tertiary carbons? Methyl. So we'll say, all right, increasing SN2 ability. All right, and then if we're looking at our E2 reactivity, is it ever going to work on a methyl? No. So in this case, E2 reactivity tends to be a little bit faster as we get towards the tertiary carbons. All right, which means when we look at these, if we take a methyl carbon and we treat it with a strong nucleophile that is also a strong base, what sort of reaction do we expect to occur? SN2 exclusively, right? There are no beta protons to allow for an elimination reaction. But then as we go over to our primary carbons, we could say, all right, it's mostly going to be SN2. But we do get a little bit of our E2 product that's minor, because we're increasing that E2 tendency. What do you think happens with secondary carbons?
Mostly E2.
Yeah, mostly E2.
And these are mixes, right?
Yeah, exactly. So we're going to get a mixture of products. And then SN2 is going to be our minor product. And then what do you think about with tertiary carbons? Only E2. Nucleophile just can't reach into a tertiary carbon, so this will be E2 only. So this is something that kind of drives me nuts when I see organic chemistry textbooks where they make it appear cut and dry, where they say this one will only do SN2, and it's like, not quite. In a lot of these cases, you're going to end up with a major and minor product mixture, and we do have to account for both of those. So let's take a look at an example reaction. And let's say we've got 2-bromopentane. And we're using sodium ethoxide. Is this a strong base, strong nucleophile, or is it both a strong base and strong nucleophile? It's a strong base and strong nucleophile, right? And if we look at our carbon, is that primary, secondary, or tertiary? So it's secondary. We've got a strong base that is also a nucleophile. So what do you think our major product is going to be? Mostly E2. So let's try to draw our various E2 products that we'll get out for this reaction. So we've had a fair amount of practice. That would be one E2 product. Is that it?
No.
What would another one be?
The double bond on the end.
A double bond on the end. So we could have one where it's like that, and there's one other one. Anybody know what the last one would be? Cis. So we could have the double bond be right there, right? All right, so we've got these three E2 products. So let's label these as E2. Which one of these is going to be our major E2 product, and why? The first one. So this one would be major. This one would be minor. And this one would be very minor. Why is the first one going to be major? Yeah, it's trans. And if we look at the small bases like sodium ethoxide prefer our Zaitsev products. And they prefer the trans Zaitsev products. Our minor one will be our Hoffman product. And then what other minor product might we get out of this reaction? Yeah, we might get a little bit of our SN2, in which case we would have an inversion of stereochemistry, and we'd end up with this product. So we could say that this would be our SN2 product, and this would also be minor. So in this reaction, it's not cut and dry, like I said. Oftentimes we end up with a mixture of products. In this case, we end up with a mixture of 4 potential products. The major one is going to be that E2 product that results in the transalkene.
So is the SN2 product less minor than the Hoffman?
That's really hard to know without having experimental results. We could predict our major products, but comparing the minor products becomes really tricky.
Okay.
Yeah, that's a good question. All right, so tomorrow what we're going to do is we're going to have an in-class worksheet that we're going to practice on together. So come prepared to work on that practice. And then if you have questions about the POD, let me know.